Good morning and good afternoon, everyone. Welcome to today's webcast, A Trillion Rows Per Second as a Baseline for Interactive Analytics. My name is Jennifer and I'll be your moderator today. Before we begin, there are just a few housekeeping items I'd like to review. This webcast is being recorded and you are currently in a listen-only mode. You may submit any questions you have throughout the webcast via the Q&A function or chat function in the lower right corner of your console. You can also follow us on Twitter at MemSQL or live tweet us during the webinar using hashtag MemSQLWebcast. We will address everyone's questions towards the end of today's presentation. After the webcast, you will receive a follow-up email with a link to the recording and slides. If you wish to contact us, please send us an email to team@memsql.com. With that said, let's begin today's webcast. Today, we will show you how to run a single analytical SQL query at over 1 trillion rows per scan rate. We will be discussing the level of concurrency and response times that's possible with MemSQL, how data architects can create business value through fast and accurate decision-making at any scale, and we'll share a few tips to keep in mind when working with a system that can provide near instant response time for analytics. With that said, I'd like to introduce today's speaker, Eric Hansen. Eric is a principal product manager here at MemSQL. He's responsible for query processing, extensibility, and geospatial feature areas. He's a PhD graduate of UC Berkeley, was an Air Force officer, a professor of computer science at the University of Florida, and a principal program manager and developer in the SQL Server team at Microsoft. He was named a high committer for contributions to Stinger. He's a technology expert on data warehousing, column stores, vectorized query execution. Thank you for joining us, Eric. You now have the floor.
All right, thanks, Jennifer. So today, as Jennifer said, I'm gonna demonstrate for you a 1 trillion rows per second scan, processing a large query against a sample data set on an Intel cluster with state-of-the-art Intel Skylake chips. So you kind of already know what the punchline of this presentation is going to be, but let me build up to it for you before we do a demonstration by first giving you some background on MemSQL. What is MemSQL? And then I'll talk about interactivity and user satisfaction when using information systems, and also I'll talk about state-of-the-art query execution technology, which is going to make my demonstration possible. Then I'll give you the demo, and then we'll talk a little bit about where we can go with this kind of technology that gives this incredible interactive response time. So a little bit about MemSQL. MemSQL is an SQL relational database system. So it supports ANSI SQL. You can do all the things that you're used to doing with SQL and filtering, joining, aggregating, grouping, and so forth. It's extremely fast. It's a very high performance system. It's a performance-oriented product. The reason it's so fast is we use scale out, so you can split the data across multiple servers and use them all in parallel. We compile queries to machine code. We make use of in-memory structures for the row store structure available in MemSQL, which I'll say a little bit about. And we use vectorized query execution, where we process data in vectors rather than single values at a time. And so there's two storage structures in MemSQL. One is an in-memory row store. This is used for transactional type applications. You can scan, filter, seek into a row store very, very efficiently. And we also have a disk-based column store. So if you've got more data than will fit in RAM, you can store as much data as you need with a column store structure. And this is very good for data warehouse type applications where it's truly analytical query processing. And as I've alluded to, MemSQL supports both transaction processing and analytics on the same SQL relational database system. So it's a general purpose system that lets you do, whatever kind of application you need to build. One thing that is amazing about MemSQL is the ability to sort of update data in real time while you're querying it. And you may have heard MemSQL referred to as a real-time database or a real-time data warehouse. So, people who've been around in the industry for a while talk about operational data stores, which store data that's been recently gathered from an operational system for additional analytical processing or transformation. And so MemSQL just so happens that it's fantastic for that type of scenario. It's sort of, nothing can touch it in terms of how well it can do that sort of operational data store scenario. So why would you want to use MemSQL? There are sort of three main benefits you get with MemSQL. One is fast data ingest. So it's extremely, easy to suck in just millions and millions of rows per second into MemSQL, and then query it as it's being loaded without really impacting your query workload. It also has very low latency. So some of the big data systems and cloud, platforms for data warehouse or big data can produce reasonably high scan rates and rates of throughput, but they have kind of an unfortunate amount of latency. So it might take a second or two minimum, maybe even more, to run a query. And as we'll discuss, that kind of latency is very perceptible to the users, and users want better than that. They want more instantaneous response time. And MemSQL supports extremely high concurrency, so you can have dozens and dozens, or even hundreds of queries running concurrently. If you size your cluster right, you have the right database design with MemSQL. So a critical part of MemSQL's high performance capability is the scale out architecture that we support. And so we have a cluster architecture where data is split across leaf nodes, and we use hash partitioning to horizontally partition data across the leaf nodes. And then there's an aggregator node that sits above the leaf nodes, and the client applications connect to the aggregator, submit their queries. The aggregator compiles them, optimizes them, and initiates and controls execution, gathers results from the leaves, and sends them back to the client after finally assembling the results. So we actually can have any number of leads, there's no limit, and also any number of aggregators. So if you have a very high concurrency workload, you're not limited by the bandwidth of one aggregator. You can have any number of aggregators as well, and your client can connect to any of the aggregators to run queries. So in order to get really fast interactive response time, there are some challenges. One is large data volume. And if you've got a lot of data, you need a lot of horsepower and very high, and very fast inner loop to get fast response time. Also, if you've got a lot of concurrent users, that'll of course impact response time because users have to share resources on the cluster. Also, query complexity impacts response time. The more joins, more aggregates, more filters, et cetera, that you have, the query can be more challenging, and that can take more time. And also, rapidly changing data can impact response time. So if you're using a database management system that where concurrency control is not architected as well as optimally as it can be, queries can block while waiting for other queries or updaters to finish. So now I wanted to talk a little bit about response time, productivity, and user satisfaction. This is a little bit of an aside from the technology itself, but it's important to understand, what response time, what the impact of response time is on users' experience with your information systems or analytical reporting systems that you're building. So before I go into the details of that, I just wanted to talk a little bit about sort of my personal story experiencing query performance. And this is, this is just my story, but it's I think a lot of people who've been around in the industry for a while and have seen how technology has changed, can appreciate this. One is, that it starts back in about 2006. I was working with SQL Server, planning new data warehouse features for SQL Server, and I experimented with what we had at the time, and I was able to get 1 or 2 million rows per second per core scan rate on a small 4-core server. And so what this really means is, you could be processing a query against say a data mart with a few 100 million rows. If you had to scan an entire fact table with a few 100 million rows, it could take minutes for that query to run. And it's a substantial amount of data, but it's not that much by today's standards. And it's minutes. You can get up and go for coffee while you're waiting for your query to run. So it's really not very satisfying. Then fast forward 6 years to SQL Server 2012, which introduced a column store feature, and it had a very fast scan rate. But at the time, the technology allowed 100 million rows per second per core scan rate, 16 cores on a server. So then on a sort of a smaller data set, like 100 or 200 million rows, you could get really pretty interactive response time, like sub-second response time. It wasn't like, you could feel how slow the queries are running, but it was kind of interactive. But again, then that was kind of a smaller data set. Then fast forward another 6 years, 2018, MemSQL, we've been able to achieve 2.5 billion rows per second per core scan rate. So that's, more than an order of magnitude faster than that previous example with SQL Server on our column store. And because it's a cluster architecture, it's economical to use much more hardware. On 448 cores, we can get queries that process tens of billions of rows in a split second, like a few hundredths of a second. So anyway, we've gone like 3 orders of magnitude every 6 years in this sort of in my personal experience with query processing performance. So technology has really changed, and it's time to reevaluate the technology choices you're using when you're building analytical systems to think about what the state-of-the-art systems can provide. And MemSQL is extremely fast and can give you amazing response time. So as I was sort of reading up on the impact of delays and waiting on user psychology, I came across this interesting quote from William James in Principles of Psychology, way back from 1890. That stimulation is the indispensable requisite for pleasure in an experience, and the feeling of bare time is the least stimulating experience we can have. All right, so that's a beautiful way of saying people find it really tedious to wait for things. So they want their results right now. So let's talk a little bit more about the user impact of response time. So users become used to very fast response time, and they expect it. And users are used to using things like Google, where they're querying like all the data on the web with a few keywords, and they get back answers in sub-second time. So if your information systems can't provide great answers in sub-second time, they question it. And there's studies that show that satisfaction increases as response time decreases. It's not surprising, but actually the interesting thing about that is that there is no lower limit of satisfaction until you get down to like 50 milliseconds. Then that appears like completely instantaneous and people can't perceive it. So fast response time is virtually always better until you get down to like 50 millisecond response time. And delays of 50 to 150 milliseconds are noticeable. They're perceivable by users. And this is based on studies about real-time applications like video gaming. But it's also true for analytical information systems that can be perceived. And just to understand sort of what the limits of human perception of time are, 250 milliseconds, that's a quarter of a second, is the median human reaction time. You'd be able to react, like press a key or move your hand based on some stimulus. And actually, it's less than that. It's about half that for the most elite human performers, like fighter pilots and pro sports stars and elite video gamers. So, down to times down at that scale, people can perceive delays. So there's some subtleties about fast response time. I'm going to show you what incredible response time MemSQL can give on very large volumes of data. But there's some subtleties here. High variance can bother users. So response time less than a quarter of the mean response time or more than twice the mean response time tends to cause users to feel like something's wrong. So it can help to give a message if the variance is going to be high. And also, unexpectedly fast results can make users apprehensive. So this is kind of surprising. Obviously, very slow results make users apprehensive, but very fast results will make them question the system, like, can that be possible? However, people will get used to it pretty quickly, so it's not a big concern. But initially, people may be surprised by it. Really fast response time for things that they perceive should be difficult. Also, fast response can lead to more input errors. And that's because people, if something takes, if a query takes a minute to run, when somebody's filling out a form to parameterize the query before they click the go button, they're going to be really careful to fill out the parameters correctly. If it takes a split second to run, they might be less careful about filling in the form before they click go. And so that's why there can be more input errors. It's just because people get a little casual or careless if things are really fast. But actually, that's not a big problem, because really fast response time makes users interact with the data and explore it more. And that creates a lot of business value. By having the data, the users, just readily think, do thought experiments with your analytical system, that's going to allow them to make insights into their business, your business, and make better decisions with their data. And that'll, the value of those decisions will greatly outweigh the cost of MemSQL. So moving on to MemSQL query execution technology. MemSQL, as I said, gives lightning fast response time because of these technologies. Scale out, as I've discussed. Also, compiled query. We compile queries to machine code rather than interpreting them like other systems. We have an in-memory row store, which is much, much faster than other row store systems that are disk-based from traditional database systems like Oracle, SQL Server, MySQL, and so forth. Also, we have a column store that's oriented towards very fast analytical performance, and we support vectorization and also use Intel SIMD instructions on the latest Intel chips for very high performance using the AVX2 instruction set. So a little bit about compilation. MemSQL compiles queries to machine code, as I said, and here's an example of running a query, a non-trivial query, which is select count star from T where color equals red, and that scans about 8 million rows. I calculated the scan rate at 24.7 million rows per second per core. I should have put million in there. It should be million rows per second per core. And compare this to 1 to 2 million rows per second per core on an interpreted disk-based row store database, which is what most of you are used to using. So we're talking, more than an order of magnitude better performance due to compilation and in-memory And this is for our row store, which is for more transactional applications, but also for real-time analytics when you're analyzing data and updating it a lot in real time. We support a disk-based column store, which breaks the data into 1 million row chunks called segments. Each column is stored in a separate file on disk. We only read the columns. You only read the columns you touch, and it's highly compressed. And we have minimum and maximum values stored for each column, for each segment, so we can do what's called segment elimination. If you've got a filter, we can check the metadata for each column and can rule out an entire million row chunk that way without having to open it up and scan it if it doesn't qualify. We support vectorization, which is processing data in 4,000 row chunks, which we call vector projections. And each chunk is stored so that each column within this 4K row chunk is stored in what's called a column vector, which is basically just an array of like 64-bit words. And then we process those arrays or vectors in a very tight loop of C code. And that gives us some tremendous performance improvements. You can get up to a few 100 million rows per second per core scanning data this way. But to get up to this 2.5 billion rows per second per core level, we had to go even beyond that. So we used Intel AVX2 SIMD or SIMD instructions. This is single instruction, multiple data. For those of you who are not familiar with SIMD, basically there's a set of 256-bit registers in the modern Intel processors, and you can pack multiple values into each register. Like, for example, you could pack 4 64-bit integers into each register and then do an instruction that operates on these 4 integers in a single instruction cycle. So, for example, you could add 2 registers and do 4 logical additions in a single instruction, producing an output register result. So we use operations on encoded data in MemSQL using Intel AVX2 SIMD, and that allows us to do filters and group by and some other operations on the compressed data format. And this is what lets us get greater than 2.5 billion, actually even greater than 3 billion rows per second per core. And this is actually done at the scan level for local filters and group by before we get to the vectorization phase. So this is the very lowest level in the query execution system, down at the scan. Just to make it clear what it means, what is encoded data, we have a number of different types of compression. One of the primary ones is dictionary encoding. So here's an example where we've got 3 different colors stored as character strings, but when we compress the data, we'll store integer ID numbers for these colors instead of the strings themselves, and it only takes 2 bits per color to represent this. And we can pack these bits into these AVX2 SIMD registers and operate on multiple 2-bit quantities in parallel in a single instruction. So now I want to move on and give you the demonstration to show you a trillion rows per second scan. And first, I want to thank our hardware partners, Intel, for giving us access to this hardware. These are brand new Intel Skylake servers that I'm going to use. And the hardware looks like this. These are Intel Xeon Platinum 8180 CPUs with 28 cores each, also known as Skylake chips. These are the Skylake chips with the largest number of cores that you can buy right now from Intel. And I'm using a configuration with 8 leaf nodes and 1 aggregator, and total number of cores at the leaf level, which is the main thing controlling the performance, is 448 cores. So the data is synthetically generated stock trades that are similar to trades on the NASDAQ stock exchange. They use NASDAQ stock symbols. We use 57.8 billion rows of synthetically generated data in this example. So how big is a trillion? So $1 trillion worth of $100 bills would cover a football field stacked 6 feet high. A trillion is the number of tweets in 5 years. the number of text messages in the world in 45 days, and it's more than the number of checkout transactions at Walmart since it was founded. It's a really big number. All right, so let's try the demonstration. Okay. I'm going to show you how many rows are in this table. Okay, it's too hard to read, so let's format it with some commas. All right, so that's 57.75 billion rows. That's a lot of data. So now I'm going to run a query. So here's a query. It says select stock symbol, count star as C from trade, which is this table, grouping by the stock symbol, order by C descending, limit 10. So what that says is, give me the top 10 most traded stocks of all time. And I've skewed it so that the higher capitalization stocks have more trades. And so let's run this. So did you see that? It came back in 0.05 of a second. It scanned the entire table and it spent time on every single row, and it came back in 0.05 of a second. So now, to get some more precision about the performance rate, I'm going to run the stored procedure profile query that runs that same query in a loop 100 times. And let's see how long it takes to run it 100 times so we can get some more significant figures. So it's 0.0533 seconds per execution. So let's see what that is in rows per second per core. Excuse me, just rows per second, the exact rows per second. So it's 1.083 trillion rows per second scan rate. So this is a real technology breakthrough that we're able to process data sets that large, that fast, and it's really going to open up some new opportunities for you as an application developer building analytical systems. So what does it mean? It means you can encourage analytical exploration of your data. People don't have to wait. You know, there's nothing holding them back from learning about the data to make great decisions that'll help your business perform better. And again, those decisions, the value of those decisions far outweigh the cost of MemSQL and the equipment. And so the technology exists to meet these kind of challenges. Expectation of interactive response time that people are used to, fraction of a second or sub-second response time, you need to give it to them. MemSQL can do that for you. The data explosion, data is, is growing exponentially year over year. As the data grows, we can handle it with scale out and very fast query execution. Higher concurrency demands, more users want to concurrently access or simultaneously access data sets. And people want to use SQL for analytics. Real-time update is important, so they need to be able to analyze the data as they're updating it, as it's trickling in, or as rows are being changed. And there's a need to run on economical hardware, which is industry standard, like the Intel hardware that I've described that we were using in the demonstration today, and also need to run anywhere, whether it's on premises or in any of the major cloud platforms. MemSQL covers all these areas. Just think about what kind of response time you can get on your data. If you want to experiment with MemSQL, go to memsql.com/download and try it out.
Great. Thank you, Eric, for the presentation and for the demo. So we've got a few questions from the audience, and I think we just have a minute or two to answer what we can. So just a reminder, you may submit questions through the Q&A function located in the lower right side of your console, or you can tweet us using #MemSQLWebcast. So let's start with kind of our first question. So how much memory is backing your 57 billion rows?
How much memory? It's a few terabytes, like 2 or 3 terabytes.
Great. Thank you. And we have another question. What was the average row length of the 2.5 billion rows per second per core use case?
About 100
Great.
bytes, 100 bytes.
And what type of data was used? Was it just business data, structure, XML, JSON, geospatial?
It was structured tabular data.
Great. And we've got another question about the demo. So in the demo, was the query cached?
No, the query result was not cached. It was actually processing every single row in that time.
Great. And we've got another question. Can this be tried on the AWS cloud?
Sure. You know, AWS has the state-of-the-art Intel chips and some of their newer VM models.
Great. And I think there's one more. What's the benefit of MemSQL versus a Hadoop cluster?
So MemSQL is really a database management system that can do transactions. You know, it has very good index support. It can do analytics. It has a buffer pool. It has an in-memory data cache. So it has concurrency control. So it's really a database management system. You know, and it's enterprise ready, and so I think that's different than what you find on the SQL systems available on the Hadoop stack.
Okay. Thank you, everybody, for the questions. So unfortunately, that's all the time we've got for today. But if you do have any additional questions that we haven't addressed, we'll be sure to follow up with you after today's webcast. So I just want to thank Eric and everybody for attending today. Just a reminder, we'll be sending you a follow-up email with a link to today's presentation and a recording. If you have any questions in the future, please send us an email to team@memsql.com. We invite you to check out some additional resources at memsql.com/resources, request a demo at memsql.com/demo, or give us a try just at memsql.com/download. So again, thank you for participating and have a great remainder of your day.